Question number 70 is about magnetic force, magnetic field, and velocity relation. For each situation below, use the movement of the positively charged particle. It's a positive charge. And direction of the magnetic force acting on it. To find the direction of the magnetic field, yani B is going to be found in this problem. Magnetic force acting on the positive charge is given. Yani each of them is positive charge in here. Positive, 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 positive. So find B direction. For positive charge, we know the palm is going to be the direction of the magnetic force. Forefinger is the magnetic field direction. Thumb is the velocity direction. If magnetic force is given, I told you let's start with magnetic force first. I will do now on the board, then I will do with your page. So I will make my pen pointing magnetic force direction. So my pen goes up to the board. Then I will check my thumb. My thumb is going out of the board, but it must be to the right of the board. So now forefinger goes into. So magnetic field must be into the page and across. Second one, again I will start with magnetic force. Magnetic force again points up to the board. Follow the board, please. Okay, magnetic force is up to the board, but thumb must be out of the board. Yes, it's
That's it.
out, already that. So as you see, my forefinger goes to the right. So to the right of the page is the magnetic field. For C, force is to the right. So as you see, my pen goes to the right. Then velocity must be into, but my velocity goes out. So now I'm going to rotate my hand, make it into. So force is to the left, thumb is into, so forefinger goes down to the page. It's going to be like that. Clear? Now let's continue the next problem. After 17, we have 18. A stream of electrons is projected horizontally to the right. Stream of electrons means thousands of electrons, billions of electrons are moving to the right, horizontally to the right. A straight conductor carrying a current is supported parallel to and above the electron stream, yani another conductor. Stream of electrons to the right, another conductor right, parallel and above. What is the effect of on the electron stream if the current in the conductor is from left to right? There are two approaches in this problem. My approach is generally considering that electron motion is also producing electric current. If electrons are moving from left to right, electric current of this electron must be right to left. So this is the electric current, direction of the electric current of the electron stream, to the left. But conductor's electric current is to the right. These two currents are opposite. If two currents are opposite, they will repel each other. Yani these electrons will be repelled by this conductor. When it's repelled, it will be deflected like this. Yani they will deflect away from the conductor. You can also use right-hand rule for single electron. It's also possible. But for electron, we are using the back of our hand. So, at the position of the electron, this wire produces electric magnetic field. So find the magnetic field of this wire in here. So electric current of the wire is to the right. Above the wire, in here it's out. But in here it must be in. So this electric current, let me call it another. This electric current produces at this location a magnetic field which is cross. External magnetic field for these electrons are going to be cross. You can go also like this. Then apply right-hand rule 3 for electron. Magnetic field, external magnetic field is cross, which is into. Velocity direction of the electrons are to the right. Look at the force acting on the electrons. Down to the page. So this force will cause each electron to move away from the conductor. Yeah, both approaches possible. But my idea is current approach is much practical. You don't need to apply right-hand rule. Only you are going to know that one current is to the right, current of the electron is to the left. opposite currents repel each other, so then electrons must move away from the conductor. Okay. Now, the same question as the B part. It says that, what is the effect if the current is reversed? Of course, if current is reversed, this current is reversed, both current becomes in the same direction. They will attract each other in this case. If they attract each other this time, electrons will be deflected towards the conductor. These electrons will be approaching the conductors. Two currents attract each other, two same directed currents attract each other. This wire will attract these electrons towards itself. B part. And question number 19. Question number 19 is related to question number 18. It says that if the conductor in item 18 is replaced by a magnet, yani remove this conductor, just put the electrons in here, and also instead of conductor, put another magnet which produces the magnetic field. It says that. If the conductor in item 8 is replaced by a magnet with a downward magnetic field. Now in here, the problem is that sometimes students get difficulty with this. When they say downward, they understand downward to the ground. But this is first set. In the first set, we don't have downward to the ground. We have down to the pitch. So even though it says downward, we should understand, yes, the question number 18 is, the set is given to the right, to the left, up to the pitch, down to the pitch. So this downward must be down to the pitch. It is down to the pitch. I will draw the magnetic field of the magnet down to the pitch, as you see. These electrons are moving inside this magnetic field, so I will apply magnetic force for acting for these electrons. So which direction magnetic field is? Downward to the voltage. In which direction electrons are moving? To the right. Look at the pen. Out. The force acting on these electrons are out. They will start approaching to us. Observer, as an observer, us. So the answer is going to be, the magnetic force acting with electrons is going to be out of the pitch, and electrons will be approaching to the observer. This is the answer. And next question, question number 25. This one is, I make a full page for this question because this question requires explanation, clear explanation. It doesn't mean that it's a very long question. Yeah, a bit longer compared to the others, but not too much. Two currents run in opposite direction in two parallel wires, A and B. There are two wires, and in these two wires there are two opposite currents. These A and B wires are separated by a distance of 1 meter apart. If the current of the IA is a third of IB, yeah, IA is equal to IB over, so this is given the question. Determine the position of the point along the line, normal to the wires where the total magnetic field is 0. First, let's think about each wire's magnetic field around. One wire will have electric current up to the page, the other one will have down to the page because they're opposite currents. It doesn't matter which one you are going to choose, up to the page or down to the page. You can do like up to the page or down to the page, it doesn't matter. You will get the same answer. I choose this one down to the page, that one up to the page. I said this one is wire A, I said this is wire B. Wire A's magnetic field around is, on the right it is out, on the left in. But this one's opposite, because electric current is opposite. On the right it is into, on the left out. I separated them first to see the magnetic fields, but normally these wires are put close to each other. How much is the distance between them? 1 meter. Now I'm going to make them close to each other. And these two wires I will put close to each other. When I put them close to each other, what will happen then? Let's see that. Between these two wires, magnetic fields are in the same direction. So is it possible same directed vectors to cancel each other? No. Now between two opposite wires, this region can never have a zero magnetic field. Even opposite, strongest magnetic field between these two. But look at the beyond the wire A's left and wire B's right. They're opposite. At least weaken each other. Maybe they will completely cancel, maybe they will weaken each other. Questions telling you that. Determine the position of the point along the line normal to the wire. Yeah, draw a normal line to the wire. On this normal line, where is the net magnetic field is 0? Is it between the wires? No, they are supporting. On the left or on the right of the wires? We will check it. Okay, now I will solve this problem. To make net magnetic field 0, two conditions must be provided. First condition, magnetic fields must be absolutely opposite in directions. So then here and here they are absolutely opposite in directions. Second one, their magnitudes must be equal. Yani magnetic field because of the wire A in here, magnetic field because of the wire B in here must be equal to in magnitude. So then two opposite vectors, equal numbers will make 0. Like positive 5, negative 5, sum of them is 0. Positive 10, negative 10, sum of them is 0. Opposite in directions but equal in magnitudes. So the magnetic fields of the wire A and B are in the opposite direction, so they weaken each other in here. Magnetic fields of wire A and B support each other in here. Magnetic fields of wire A and B weaken each other here. But the point is this. This point is going to be in here on the right side or on the left side. So how can we decide this? On the right or on the left side? Here's a key information for this. Net magnetic field will be 0, always closer to the smaller current. Which one is smaller current? Its side. That point it is. Which one is smaller current? A or B? A or B? A, because A is AB over 3. This is AB. If you give a number, for example, if it's 3, this is 3 over 3, which is 1. Then it's going to be closer to small current. It will be somewhere in here. Somewhere in here. I will say this distance x. Mathematical known as x. Then I will write magnetic field for each wire at this point. So condition 1, the total magnetic field is 0 where the magnetic fields are opposite in directions. Here is the point. Second condition, condition 2, the net magnetic field is 0 at a point B beyond the wire, which carries a smaller current, and point B must be beyond wire A. So that also their magnitudes must be equal to each other. Then I'm going to write their magnitudes. This point is at a distance of x from wire A, at a distance of 1 plus x from wire B, because this distance is how much given in the question? 1 meter. So magnetic field of wire B, magnetic field of wire B is going to be mu over 2 pi, because it's straight wire, I over d. What is I for wire B? I am going to say IB. What is distance from wire B until this point? 1 plus x, 1 meter plus x. So then, at this point also wire A produces a magnetic field, which is mu over 2 pi, IA over distance. What is distance? Only x. IA over x, but IA is equal to how much? IB over 3. In the question is given. So instead of IA, I am going to write IB over 3. Then I will make simplification. From this point on, go with simplification. Let's do it. Mu over 2 pi, simplified. IB and IB, simplified. What is that in here? 1 over 1 plus x. 1 over, even IB is simple, 1 over 1 plus x. What is left in here? This 3 goes into the denominator, 1 over 3x. 1 over 3x. The rest of them is cross multiplication and solve it. So 3x is equal to 1 plus x, transfer x other side, 3x minus x, which is 2x. 2x is equal to 1, x is going to be 0.5. And this wire is going to be, this point is going to be 0.5 meter from wire A, 1.5 meter from wire B. Peki. Can we do a hack for this? Should we do the hack for this? So there are two wires. They have electric currents opposite in direction. One of them electric current is I, the other one is 3I. Magnetic field is going to be 0 at a point closer to smaller one. In here, magnitude of the magnetic fields must be equal to each other. Magnitudes must be equal to each other. But I know magnitude of the magnetic field is proportional to I over D. Huh? To be B equal, by what factor electric current increases, its distance must increase the same factor. If I say this distance x, that distance is going to be in the ratio of their electric currents. So because I to the I multiplied by 3, you should multiply this x by 3. So this distance is given as 1 meter. Then mathematically I will write that. What am I going to write? 1 plus x is equal to 3x. Then transfer this other side. 2x is going to be 1. X is going to be 1 over 3 and 0.5 meter. And this distance must be 0.5 meter. Right in here, net magnetic field is 0. Okay. And next question is related to this one, but let's remember something before starting next question. When two electric currents, two wires carry electric current in opposite directions, what did we learn? Magnetic field between them can never be 0 because they are supporting each other. But on the right and on the left, they weaken each other. At one point, it can be 0, but currents are opposite in direction. Now, this information will be used in next problem now coming. Is this? Two wires carrying equal but opposite currents. Opposite currents are twisted together. Twisted means like this. Hold the wires like this, and then twist them like this around one another. Twist it. The wires are twisted now. In the construction of a circuit, why does this technique reduce strength of magnetic fields? Maybe if you check your home around the wires in your home, you are going to see that they are twisted like this. Because one of them takes the electric current from city to your house, the other one house to back to where the original of this. Yani, one of them is this direction, the other one is that direction. They're opposite directed currents they carry. Why they are twisted together? They are asking about it. When we twist them together, what happens to get that? One wire's electric current is cross, the other one is that. Cross one produces a clockwise magnetic field. Everywhere. Red, the other one produces counterclockwise magnetic field everywhere. Look at between the wires. These two magnetic fields are in the same, but on the right and on the left, look at their directions.
Same. No, they're opposite.
How? On the right and on the left, blue and green. Blue goes up, red goes down. Blue goes up, red goes down. They are not. Between the wires, they are supporting each other, but beyond the wires, they cancel each other. They are weakening each other. When we twist them together, what is happening the distance between the wires? Decreasing and finally becomes 0. You are making the area or volume, which is magnetic support each other, 0. But outside the wires, they are opposite. They will make cancel each other 0. Yani around this twisted wire, net magnetic field is going to be 0. But if you keep them like this, not twisted, between them, they support each other. On the right, just single point. One point is net magnetic field 0, but other points, weak but still exist. But if we make them stick each other and then twist it, net magnetic field everywhere is going to be 0. That's why they are doing these wires twisted for carrying electricity from one place to
Another place.
to protect the harmful effect the electromagnetic magnetic waves. Other living things can be human or animals. Magnetic field in all case not healthy for us. Okay. Next question. A proton moves eastward in the plane of Earth's magnetic equator. Can you switch it on, please? A proton moves eastward, yani east, in the plane of the Earth's magnetic equator, where Earth's magnetic field points north. And magnitude is 5 times 10 to the negative 5 Tesla. What velocity must the proton have for magnetic force to just cancel gravitational force? Now, when electrons moving horizontal to the Earth, this is the set of direction. Let's draw the set of direction. North, south, east, and west. It says that, proton, this proton moves eastward. Yani velocity direction is to the east. Magnetic field is to the north. Let's find the force acting on the proton. It is east. This is going to the north, according to your page test read. My board is vertical, your page is horizontal. Electron goes, magnetic field is to the north. Electron goes to the east. Look at the force. Upward. What does this upward force do? It is in the opposite direction of the gravitational force. Gravitational force takes the object down, but magnetic force pulls the object up. If we want to cancel gravitational force, what should happen? They should have equal in magnitude. In this case, they cancel each other. Yani, magnetic force must be equal to gravitational force, then they will cancel. The question for magnetic force, Q, V, B. The question for gravitational force, M times G. Then, velocity is the question. Find the velocity. V is equal to mg divided by qv. M of the proton, it must be given, I forgot to write, I think.
QB.
Q, M of qv, yeah.
B,
Or
B.
qb, sorry. M of the proton will be given in the problem. How much was it given? Tell me the number in that question.
5 times 10 to the 5.
5 times what?
No.
Mass of the proton.
1.67
1.67 times 10 to the power negative 29, I think, huh? 27 times G is 9.81 divided by Q 1.6 times 10 to the power of negative 19 times
5 times 10 to the power negative 5. 2 times.
how much is the answer then? B 2 times
Negative 3.
negative
3.
3 meter per second. So this is how we solve this problem. In here, some students don't know this. What does this mean? To cancel gravitational force means gravitational force is downward, magnetic force must be upward to the sky. So then, but they must be equal in magnitude to cancel. So when you make the magnitude equal, then you will find the answer. Question 22 is very similar to this one also, but not charged, wire. A thin 1 meter long copper rod in a uniform magnetic field has a mass of 50 grams. When the rod carries a current of 0.245 ampere, it floats. This is the keyword. Floats and canceling is the same thing. Gravitational force should be cancelled by magnetic force, so it will start floating. Floating is generally taught by the water. When objects are staying on the surface of the water, we say it's floating. How it floats? Gravitational force cancelled by upthrust of the water, so the net force becomes 0. So same thing will happen in here. Gravitational force acting on the rod must be cancelled by magnetic force acting by the on the rod. In this case, net force is going to be 0. It will float. Then write them equal to each other. F magnetic is equal to Fg. Magnetic force BIL. Fg is m times g. What is the question? Find the field strength. Can B is the question. Transfer IL other side. B becomes mg over IL. Now, so let's write everything. M is given 50 gram. Convert to kilogram, 0.05 kilogram times 9.81 divided by electric current is 245. Length is how much?
1.
Yes, this question is repeat question several times, 3 or minimum 2, more than 2 maybe. The result is going to be 2 Tesla. As you see, this magnetic field is very strong at that location. And question number 23. We did this in the classroom in detail, so no need to do it again. We will go with 24. A proton moves at 2.5 times 10 to the power 6 meter per second horizontally at right angle to a magnetic field. Right angle means maximum magnetic force acts on it, QVB. We are going to use QVB if required. And this is V. We know it's a proton, Q for proton 1.6 times 10 to the power negative 19. We will use. What is the strength of the magnetic field required? Again, exactly balanced. 3 questions are same logic. Cancel gravitational force, floating, and balance. Exactly balance. Exactly balance the weight of the proton to keep it moving horizontal, because net force acting on the object is equal to 0. Object follows a horizontal path. In 1-3 we learned law of inertia. Yeah, this question tells you that proton will have a gravitational force Fg, which is m times g. If you want exactly balance this, magnetic force must be upward to the sky. F magnetic must be upward to the sky. So if I want this proton to follow horizontal path, these 2 forces must cancel each other. To cancel, their magnitude must be equal to each other. Then I will continue. F magnetic is equal to F times G. F magnetic is QVB. Gravitational force M times G. What is question? Strength of the magnetic field. B is question again. Divide both sides QV. B is equal to mg divided by QV. M is given in the question. 1.67 times 10 to the power of negative 27. G is 9.81 divided by Q is for electron 1.6 times 10 to the power negative 19. V is given in the question as 2.5 times 10 to the power of 6, but don't forget to use bracket. B is going to be 4
times 10 to the power negative 40.
4 times
4 times 10 to the power negative 40.
negative 40. 14 Tesla. Okay. What about magnetic field direction? In which direction should it be? Here direction is not given. It must be horizontal. If force will be vertical, so the next question is about that. If the force is vertical, magnetic field should be
Horizontal.
because force is perpendicular to magnetic field all the time.
Yes.
So this question B talks about that. Should the direction of the magnetic field be horizontal or vertical? And force and magnetic field can never be in the same direction. They are always perpendicular to each other. Because force is vertical, magnetic field should be horizontal.
Horizontal.